Well, I'm highly honored to give talk in front of math people. some are from computer science, but well, this talk will consist of 3 parts mostly. The first, I will give some brief introduction on what is computational geometry, and then we'll talk on geometric shape matching. And as a typical example of geometric shape matching, I will give I'll present some problem called discrete Frechet distance problem. Okay. First of all, I'm a computer scientist, so I'm obliged to give you some idea on what is computation and so on. So let me start with this example. So this is Daejeon City, and you have coffee shops there. And if all the conditions, well, the coffee quality and service and the reachability are the same, then this coffee shop will partition the city into regions, which is called some cells dominated by those coffee shops. So typically, if you are a customer living here or working here and you want to drink coffee, then you will come to this coffee shop. Okay. And you want to open another coffee shop there. If you are a CEO of some coffee company, Coffee Prince company, for example, then you want to open another coffee shop there. And the size of the region, the cell, actually resembles the profit you can make from the coffee shop. So if you place your new coffee shop there, then you can occupy this region, which means that you can have that much profit. If you place the coffee shop there, then you can have that much profit there, placing there. And this is so-called Voronoi diagram in computer science. Actually, the Voronoi himself is a mathematician, and I think you may have heard about his name, the Voronoi. He's a Russian mathematician, I think, right? So it's called the Voronoi diagram, and the Voronoi diagram itself has some properties. The Voronoi diagram can be defined like this. So if you consider 2 points, here P and Q, 2 coffee shops, and you can define their bisector. So bisector means that you connect P and Q by line segments, and you take a perpendicular line between P and Q, perpendicular to the line segment, and with equidistance between them. Then this gray region is a kind of dominating half plane of P, because any point in the gray region is closer to P than to Q. Right? Then what is the Voronoi region of the P? Well, it can be defined by the intersection of these dominating half planes. Right? So from P and Q, we can define dominating half plane of P with respect to Q can be defined like this. And then for all other points, you can define such a half planes and you take intersection of them. Then this is called Voronoi diagram officially. Well, if you have n points in the plane, then you have n cells, n regions in the plane. And each Voronoi region is convex. And some other properties I'm missing. The number of edges, number of Voronoi edges, or number of Voronoi vertices. Well, this one is called Voronoi vertices, and this is Voronoi edge. The number of Voronoi edges and number of Voronoi vertices are linear. Linear means that we have n points, then there are at most c times n edges or Voronoi vertices, where c is some constant, fixed constant. So this is a typical one important concept in computational geometry or discrete geometry or so on. Then what is discrete geometry? Discrete geometry is also known as combinatorial geometry. Combinatorics means you count the number of objects. So we take the input as input the geometry object like points, lines, circles, line segments, and polygons or polytopes, and so on in higher dimensions. And we only handle a finite set of those geometry objects, say n lines or n points. And then you want to find some properties of those geometry objects. For example, we have n lines in the plane. Then you want to know how many regions do you have in the arrangement of n lines. And this is a very fundamental and typical easy question. And another question you can consider is that, okay, you add another line there, the thick line, horizontal line. And you wanna calculate or you wanna bound the number of faces in the zone of the line. So zone can be defined like as a set of points in the plane which can be seen from this line directly, from this line, which means that this is the zone of this horizontal line.
So you mean how many does this line intersect? How many?
Not only lines, but the phase means that yes, the phase is yes. Yeah. So zero phase or one phase, two phase. The zero phase is these intersection points, yes. And one phase is these edges. Two phase is simply the region itself. Then how many phases are there in the zone of the line? This is typical discrete geometry question, and the answer is still c times of n, the linear. If you have n lines, then the zone size is simply linear. And this is typical discrete geometry question. Okay. Then the computational geometry can be defined like this. You solve some problems in discrete geometry, but in computational point of view. Okay. Then I need to define what is computational point of view and what is efficient algorithm solve. Okay. In computer science point of view. Really. Computational means that you use computer. You use computer to solve the problem. So you design an algorithm, and maybe with the data structures too, that runs on a computer. And that algorithm are supposed to solve the problem itself. Then what is efficient means here? What efficient means here? So you basically in computer science, we assume that all the Bayesian operations, each Bayesian operation simply takes a single computation time. So 1 unit of time, say. Then the efficiency of some algorithm is can be measured by number of Bayesian operations it performs. So how many Bayesian operations does the algorithm perform to solve that problem? This is so-called the time complexity of some algorithm, of an algorithm. Okay. Okay, Bayesian operation means the addition, subtraction, multiplication, and assignment, and load, or something. Those kind of things are called Bayesian operations. So you simply count the number of Bayesian operations there. Okay. Then we can compare two algorithms. Which one is faster? Which one is more efficient? Depending on the number of the Bayesian operations. But when we count the number of Bayesian operations, we count them in terms of imprecise. I just used the c times of n in the previous slides. So n is the number of input or size of input. For example, n points in the plane or in Euclidean space, or a polygon with n vertices in total. Those kind of things are called imprecise. So we only use asymptotic time complexity, not exact one. So if there are n points, then our algorithm may execute around c times of n basic operations, or at most C times of n basic operations for with some constant C, then we can call the algorithm takes only linear time. If we need n square, roughly speaking, n square basic operations, then it's quadratic time complexity. Okay, so let's look at some tables here. So we have several different algorithms. One algorithm takes only n time, and there is another algorithm which takes n factorial time, and also we can consider another algorithm that takes n cubic time, n square. I'll show you why n cubic is not practical. So if there are only 10 points in the plane, then those algorithms can answer the question in less than 1 second mostly. But same algorithm can solve on different size of points. We have 30 points in the plane. Okay, still okay, except the n factorial algorithm. 10 to the 25th years. It's nonsense, right? What about this? Well, nowadays 1 million is actually considered as a small size, mostly, even. But if you look at this column, n cubic algorithm, then already when n is 10,000, it takes 12 days with some very, very fast 4-core CPU, even 32 years, and we'll die first, right? Before getting the answer. So n cubic is already impractical in most cases.
Very long is more than 10 to 20.
Yes, very long. We cannot even measure, or nonsense to measure the time complexity, and so on. So n square is still okay, right? So there is some boundary here. Well, most of algorithms up to here is called polynomial time. But already n cubic is quite impractical in most cases. So we need to design efficient algorithms. That takes less time. Okay. This is called computational efficiency. Right. Okay. Then let me introduce another typical concept of computational geometry, let's say. Convex hull of a point in the plane can be defined as the smallest convex set containing S. So if you have a set of points in the plane, then you can consider this large one as also a convex set containing S, and also can consider this one as a convex set containing S. But what is the smallest convex set containing S? The smallest convex set containing S is called the convex hull of the point set. Well, by intuition, you can consider this. You have a rubber band that contains all the points, and then you let it go. Then you have the smallest convex set containing S, right? And this is convex hull. And very nice, very good concept. But how to compute this efficiently? Well, we need some property, right? So one easy property is that, well, okay, yeah, this is input and output. This is not important actually. Okay, one property is that if you consider 2 points, from the input you consider 2 points, and then you draw a line. If all the other points lie in one side, one half plane of the line, then these 2 points must be on the convex hull, and they must be consecutive on the convex hull. Consecutive means that if you walk around the convex hull, then they appear consecutively. Okay, this is very nice property, right? So we want to make use of this property. Then how many candidates do you need to test? And choose 2. For every pair of points, we need to draw a line. Okay, so and choose 2. And we still need to test for all the other points where they lie in one side or not. Right? So probably the test takes linear time, n time. So n choose 2 times n means n cubic time algorithm. Right? But can you improve the time complexity of this algorithm? Well, of course, we already made use of nice property. Well, here is another property that gives us very nice idea. So we first sort the points along x-axis by the x-coordinates. Then we have a sorted list of points. And what I do is, well, I start from the leftmost point, and I will walk along these points in order, and I will always look at the last 3 points. If the last 3 points makes a right turn, then it's okay. If the last 3 points makes left turn, then clearly the midpoint must be away. If you consider only the upper convexal, right? For example, if you consider upper convexal, then, well, this one already makes a left turn. Then you remove the middle vertex. Right? So let's continue with this idea. Okay. Now it's convex right turn, right? So it's okay. So we move to next point. Okay. The last 3 points make left turn. Okay. Remove middle one. Okay, last 3 points makes left turn. We remove middle one. Okay, remove middle one. We continue. Okay, remove middle one. And we continue. Okay, remove. Continue. Well, it's okay, right? But we still need to continue. Okay, middle one. At the middle one we make a left turn, so we need to remove it. Oh. Again, we need to remove the last one, the middle one. Oh, again, we need to remove the middle one. And then we continue. Sorry. Then so on. So if you continue like this, then we can get the upper chain of the convexal. Why? We can prove this, right? I'm not going to show you the proof, but you can prove this. Well, if you continue like this, then you can get the upper hull, at least. Then for lower hull, you simply work backward, and then do the same thing. Okay, so you are now sure that it correctly computes the convexal. Then we need to compare their time complexity, the n cubic and this one. So how long does it take? We first need to sort them along x-coordinate, right? So sorting, well, we must say sorting takes and log n time. Well, it's very known that we cannot do it better, right? So and log n time. Then once it is sorted, we work along the list, sorted list, and check last 3 points. Okay? So first we visit each point once. Okay? Then we may remove a point, right? But we only remove that point once. Once we remove the point, then it's done, right? So for each point, if you sit on a point, then the point is visited once and removed once. Is it correct? Okay. So roughly speaking, each point is visited only twice, so on. Actually, a few more times, but still 4 times or so in all the cases. So 4 times of n, right? We need plus 4 times of n computation time to compute.
When you have, I mean, the last case there,
Yeah.
you remove one vertex and then you have to look at it again and
Yes.
remove again.
Yes.
Could that happen that you remove several vertices, so you have to track back all the way?
Yes, that's possible. But if you look, if you have the point of, if you have if you sit on the point, then the point is one point. Then the point is visited once, and removed only once.
Oh, I see. So,
Right. So point-wise counting would give you only around 4 times, and we have n points there. You cannot go backward and forward, because while you go backward,
Or you visit it,
yes,
keep it,
yes,
and then
on the backward it will be removed.
yeah.
Yes, then you don't consider it as
you won't have to
anymore.
see it anymore.
Yes. Yeah. So, in total, can say that in this case, can simply say that we go n log n, because there is some constant factor is missing, but n is smaller than n log n anyway. So n log n, which is almost linear. Right? Even n is million, the log n is very small. Right? So you can say that this is almost linear, near linear time complexity. So it's a really dramatic improvement over the computation time. This is one typical example in computational geometry. So we need to find some property from discrete geometry point of view, and then we make use of this property into the algorithm. Well, to design the efficient algorithm. So this is computational geometry, so called. Okay, then let me move to geometric frame matching here. So geometric frame matching means that you have geometric shapes, basically. So you have two geometric objects, and you want to compute their similarity, how similar they are. But the typical question is that, my son looks similar to me or not. It depends on some taste, right? So we need some more concrete measure called geometric similarity measure. Right? So we are given two shapes, two objects, and usually we apply some transformation there. Well, translation, rotation, or scaling even, then we measure how similar they are. Okay? Well, most basically, for example, in this case, you are given two convex polygons. And the question is, are they similar? Well, under which measure? Well, we can define some measure, but one of them can be the maximum overlap of them. If their overlap is large enough, then they look similar. If their overlap is very small, the maximum overlap is very small, then they look quite different. For example, so if one object is round, more or less, and the other one is long, stick-like object, then the intersection itself is very small, right? Then we can say that, compared to their original size, so we can say that they don't look similar in this case. So under maximum overlap measure, we can consider translation as a transformation. So if you are only allowed to use translation, and you find their maximum overlap, and then the overlap size is the measure of their similarity in this case. Or you can consider rigid motion. Rigid motion is a combination of translation and rotation, and you want to measure their maximum overlap, and if they overlap as much, quite much, then they look similar. So the typical question is, okay, then find the maximum overlap between two convex polygons. Then we need to design an algorithm, right? Okay. Under translation, you are given two convex polygons. Find a translation that maximizes their overlap, right? Well, this doesn't look difficult to mathematicians because you already have all the vortices and their coordinates, and then you can solve some equation, right? But the problem is that, well, first of all, the computer must solve it, and how many Bayes operations do we need to solve the equation? Right? In this sense, well, we need to design some algorithm to compute the maximum, the translation, which realize the maximum rep. And there is n-log n time algorithm for this translation case. And it's the total number of vertices of the two polygons. Well, what about for rigid motion? Well, I will talk more in details later, but we don't have any exact algorithm yet, any polynomial time exact algorithm yet. This is a question. Well, there can be another measure. So if you have more than two objects, then you wanna stack them together, and the measure can be, in this case, the measure can be maximum area of the convex hull. You already know what is convex hull, right? So, under translation, for example, in this case, under translation, you stack them together. And you stack them together nicely such that their convex hull has minimum area over all possible translations. Or their perimeter must be minimized over all translations. So algorithmic question is, well, find their translations. Well, because we have in the input we have 3 objects, so we need only 2 translations, right? One is fixed and the other 2 must be translated. And you need to find the 2 translations, one for C2 and one for C3, that realize this minimum area or minimum perimeter of the convex hull.
Well, clearly your input only needs to be convex sets.
Not necessarily in this case.
Really?
Because if you are given a non-convex
what is it?
Non-convex object, and you only take simply convex hull of the object and then make use of it, right? That's enough. For this problem, the input doesn't need to be convex. For this problem.
No, but wouldn't the answer? Couldn't you assume they were convex because?
Yeah, that's what.
Yes, that's what I mean.
That's
So,
the right answer.
Yeah.
Yes. The same algorithm can compute.
I mean, if you took the convex hull of each of these,
right,
the translation vectors in the end,
yes,
the same as for
right.
these
Anyway, in the final answer, we only consider their convex hull, right?
Mm-hmm.
So we simply take convex hull of each object and then work on their convex hulls. Yes, right. Right. And for this problem, we have solution on the translation. It's almost linear again. But what about if you are allowed to rotate?
How can you talk about similarity between objects without considering scale?
Well, here we don't allow scaling because then the size or whatever, it doesn't make sense, right? Because size of convex hull can become 0 even by scaling down to a point. Right?
But your son and you looks very similar.
Right. Yeah, in that case, probably you need to apply some other geometric similarity measures, not the area or perimeter or whatever, but some other things. But under this geometric similarity measure, we shouldn't allow the scaling. Yeah, right.
Oh, so when here you're saying minimize the area or the perimeter?
Yeah. Oh, no. 2 problems.
These are 2 problems?
Yeah, 2 problems.
Oh, okay.
No, the answer is different.
Over perimeter or something.
Yeah, there are 2 different problems. The answers are different. Answers are different. So either you minimize the area or you minimize perimeter. So the answers are different depending on whether it is area or perimeter. So for this problem, we already have almost linear time algorithm again. But what about rigid motion? if you apply the rotation, you are allowed to rotate the object. We don't know how to solve this. And we only know the approximate solution in this case. This is so-called the geometric chain matching. So we are given two geometric objects, and you also already have a geometric similarity measure, and you need to compute their similarity based on these similarity measures. Okay. And for this maximum overlap problem, we only have 1 minus epsilon approximation algorithm that runs quite fast. What does it mean, 1 minus epsilon? So our goal is to find some rigid motion rho, right? And let's say that rho star is the optimum solution. Right? We have two convex sets, C1 and C2. So let's assume that C2 is fixed, stationary, and we apply this transformation on C1. Then, this is the maximum overlap. Right? We apply the transformation to C1, and we take C2, and we take their intersection. And this is the size of the intersection. This is the optimal solution, right? And our approximation, 1 minus epsilon approximation algorithm returns another transformation, rho prime, for C1, such that the solution of our approximation is at least 1 times epsilon of the optimal solution. So if our algorithm always find this kind of rho prime, then it is called 1 minus epsilon approximation in this case. Okay. And epsilon itself here is an input to the algorithm. So you can adjust how good the approximation must be in this case. But we still don't know how to solve it exactly under rigid motion.
So that's a p-task or?
We don't have any solution, any idea, any clue.
Okay.
Yeah. This is called the FP-task, actually. Yeah, fully polynomial time approximation scheme. Okay. Yeah, right. Okay, these problems are typical problems in geometric chain matching, and well, let me skip this slides because this is not that important. This is how we solve the problem in approximate way. So let me move to Frechet distance. Okay. So another geometric chain matching problem, typical one, is that we are given two curves. One curve is given like this, and the other curve is given like this, for example. This is A, and this is B. We are given two curves in the plane. How similar they are, again. And what would be the right measure of their similarity? The two curves. Well, there can be many ways to define for similarity measures, but what would be the best one? Okay.
Just translate it.
Yeah, that would be also one only if you allow translation, right? But let's say if you already translate the one curve, and let's say this is final embedding already, then you need to measure the distance, basically, right? Like the maximum overlap or minimum perimeter or whatever, you need to measure the distance. What would be the distance? there are two famous measures. One is called Hausdorff distance measure, and the other one is called Frechet distance measure. Frechet, right? Distance measure. And well, informally speaking, it's like this. You are a man, human being, walking along one curve, starting from one endpoint, and you walk along the curve, and you are supposed to reach that endpoint. But you are walking a dog, and B is curve for dog. Dog, well, in the beginning, dog is there in the one endpoint, and he is also supposed to walk along the curve and reach the other endpoint. What Hausdorff distance means that, well, because you are standing here, right? And dog is there. I don't know how to draw a dog here, but you need to connect the dog with you using leash, right? And you walk dog along the path, but on the Hausdorff distance, you are allowed to move forward and backward. It doesn't matter. You go and move back and go, and this is typical way of dog walking, right? Dog is also moving, go forward, backward, and so on. And in the end, dog must be there, and you must be here. Okay? Then, on the Hausdorff distance, the question is, what is the minimum leash length that makes this work possible? Okay? The minimum leash length is defined as Hausdorff distance of two curves.
Is it clear that the minimum is achieved? I mean, should I say it's infimum or minimum?
The infimum of a maximum distance, how to say, the coupling distance. Yeah. So you need to make the work possible. But if you say simply, well, this is crossing, so well, only zero distance would be possible. But you cannot reach the final endpoints, right? You are supposed to reach the final endpoints. Then you need some distance. For example, in this case, probably something like this distance would be okay. Right? You must somehow go forward and backward and so on. Then you can reach the final endpoint. On the Frechet distance, you must go forward. No way to move backward. You are allowed to be stationary, but you need to go anyway. You can have infinite speed, but not less than zero. Okay. This is called Frechet distance. Okay. So this is a more formal mathematical formulation of the Frechet distance. So this is infimum of the maximum distance. So maximum means that, well, what is the maximum distance between 2 points here? And you take over all possible, there are reparameterizations, right? Infinite number of reparameterizations. And among all those reparameterizations, you need to take infimum of all possible maximum value. This is Frechet distance. And of course, we cannot compute the Frechet distance between some curve, not arbitrary curves. But easiest one is you are given polygonal curves. Yeah. Two curves are polygonal, then you can compute their Frechet distance using so-called free space diagram. And okay, if I have time, then I can talk more on how to compute this. But for two polygonal curves, you can compute their distance, Frechet distance, in n squared time, roughly speaking. If one curve has n endpoints, n vertices, and the other curve has m vertices, then it takes mn log mn time. roughly speaking. So you can say that roughly n squared time it takes. This is Frechet distance.
Mn log
Mn log Mn.
Mn.
Yeah. N is the number of vertices on one curve, and n is the number of vertices in the other curve. And here is another thing, discrete Frechet distance. Discrete Frechet distance means that, well, you are given two sequences of points, but you don't consider the edgy part. You only consider vertices. You still need to follow the sequence, but you jump to the next vertex. Okay? This is so-called Frechet distance. So you measure the distance between only vertices. Yeah. Well, for this problem, we can also solve roughly the same time, Mn time, and so on. But you can consider another problem. So dog is walking along the curve, but there's no such a dog that follows this curve precisely, right? He moves around and around and around, right? So we can model that problem like this. Instead of this precise polygonal chain, dog is working like that. Okay? In this spot, dog is somewhere here. In this vertex, dog is somewhere there, but we don't know where he is actually. So instead of being given a sequence of n points, we are given m disks, and there is exactly 1 point in each disk, but we don't know where it is, and we need to measure their discrete Frechet distance.
The curve for Poisson is given?
Yeah, for human being, it's precise. Dog, well, unpredictable, right? So imprecise. We don't know where he is. But somewhere there, the dog is there. But you don't know exactly. Right? Then we cannot compute Frechet distance, actually, in this case, because we don't know where the dog is, right? But the only thing we know is that, well, we can bound. Sorry. But before that. So for example, dog can be there, right? For each disk, there is one dog, right? This is one possible placement of dogs in this case.
And you're thinking about discrete version.
Yes, still discrete version. And we need to do is, we want to find their bound. What can be the minimum possible Frechet distance? What can be the maximum possible Frechet distance in this situation? This is our question. Is it clear? Okay. If we place the red points like this, then this is a so-called acceptable sequence, because in each ball there's 1 point only, exactly 1 point. Then it's called acceptable sequence. And for this sequence, we can measure their discrete Frechet distance using trivial algorithm, right? But the question is, we don't know where it is. So we need to find the minimum Frechet distance, minimum possible Frechet distance. So basically, for minimum case, you can place these red points, and you want to minimize the discrete Frechet distance. For the maximum case, your enemy places those points to maximize the Frechet distance, but you don't know where it is, right? So you need to guarantee that, well, this Frechet distance is enough to cover all the cases. Okay, so let me first explain the minimum case. So find the minimum discrete Frechet distance over all acceptable sequences, and there are infinite number of acceptable sequences. Right? So we need to find the minimum possible Frechet distance. Okay, we need to find some properties here to design the algorithm. So before, we can consider before answering the question, we can consider this decision version of the problem. Decision version. So we give some fixed real value delta, the positive or non-negative value delta, and we want to get an answer to this question. Whether this minimum possible, well, it must be f star, sorry. This minimum possible phase distance is smaller than delta or larger than delta. So we first need to consider this question. So we give delta as a candidate for the minimum possible phase distance. And our algorithm must answer yes or no. This is decision version of the problem. Okay, we can answer this question easily. How? Well, this is a dog disk, and these blue points are human vertices. Because we are given delta value, so we draw delta disk around human vertices. Then it partitions these disks partition the dog disk into regions, right? So let's consider this case. So dog is here, right? And we can answer the question yes or no. What about this case? Dog moved to here. The answer is different or same? The answer must be same, right? Because we partition the space, the dog disk, into regions which has the same property. It doesn't cross the boundary of this delta disk. So the answer must be same, right? So we only have finite number of candidates instead of infinite number of dog placement, right? So we had infinite number of acceptable sequences, but for this decision problem, we only have finite number of placement. Right? This is already great improvement from the infinite to finite. Right? So how many reasons do we have? If you have n unit disks, then we can have roughly n square reasons. Right? If you put together them, and then you can have n square regions. So each dog region can have n square regions. How many dog disks? We have m dog disks. So n square times m regions we have, right? So we test them all.
Does it make sense that you consider AQ?
Yeah.
Because AQ is in the circle
Yes.
of AR.
AQ is in the circle. Yeah, it's okay. Yeah.
AQ in the circle of AR, and
Yeah.
so why don't you consider just the 2 points AR and AP, because they
These are human vertices.
yeah, but AQ considering AQ may not make a difference. If you ignore AQ but just to consider AR and AP, that may.
But they should follow the sequence of the connection.
Yeah.
So the coupling must be done in sequence. Right.
So if a dog is, if dog goes to a disk, then
Yeah.
does the dog stay at the same point?
Yeah, we assume that. But we don't know where it is.
So you
Yeah.
cannot change
Yeah.
point inside.
Yes. But dog placement can be infinite before, but now, well, we only have number of regions, finite number of regions, and we only need to consider those regions to answer this decision problem. Okay. And for this case, we can apply so-called dynamic programming in computer science, in algorithms. Probably, I don't have time to explain what is dynamic programming because it takes usually around 2 weeks to explain everything. But you make use of tables, and we compute the answers to each entry one by one and line by line. And when we compute the answer to one specific cell, we look at the previous solutions, and then answer to the question. Actually, that's called dynamic programming. And you can solve this problem, roughly speaking, in nm, log nm, or so on. This question. Okay, we know how to answer this decision problem. So we give delta, then the algorithm says yes or no, right? But we need to find the optimum delta, right? Still, we don't know where is optimum delta. But the answer is, well, for the delta values, there are also finite number of candidates for delta values. Why? Sorry, this is okay. Why? How many candidates of delta values do we need to test? Well, imagine that delta is 0. So the dog placement, disks are simply points, a sequence of points. Okay. Now you increase delta value from 0 to some value. Then what? There is some changes, topological, combinatorial changes. For example, here, at certain delta value, this blue disk, delta disk, may touch the dog disk. Why it is important? Because if you increase delta value slightly more, then you have new cell in the arrangement, right? As I told you before, the cell itself, if you have a cell, then it doesn't matter where the dog is, right? So once you create one new cell, then it matters actually. Before there's no cell, but now you have new cell. Then there is some combinatorial change. Right? This is a typical combinatorial change. If you increase delta value further, then two delta disks may in contact, may touch each other. If you move further, then two blue disks and dog disk may coincide. Right? If you move further, then three blue disks may coincide. These are the only events that may happen while you increase the delta values.
So in between, there's radius 1 where the first event happened and radius 2 where the second happened.
Yes.
Essentially the arrangement, when you just look at the brown disk and you look at the arrangement of these blue curves,
yes.
combinatorially they're exactly the same.
Right.
So check any one of those. Right?
Yes, exactly. So we have how many candidate values of delta in that case? Well, three blue disks coincide, right? So we choose 3 points from the human path, and then we have specific delta value, right? Right? We know what is delta value for this case. Once you select 3 vertices, right? Exactly. Well, you know what delta value it is. It must be. You know what delta value must be. You know what delta value must be. So how many delta values do you have? Roughly a cubic, right? So there are finite number of delta values. Okay. So we can compute all delta values first, because in the same time, right? So it's in roughly n cubic time, we can compute all the delta values. And then what we do is, well, we sort them in increasing order, and then apply binary search using the previous decision algorithm. So you have sorted delta values, and in the middle you call the decision algorithm. If it says yes, then you can reduce delta values by the half of the first half. If it says no, then you need to increase delta values, and you can throw away the half of delta values immediately. Right? So the number of binary searches must be log nm. Log n. Oh, sorry. Right. So if you put together, then well, there are that many candidates for the delta values, and our optimization algorithm calls the decision algorithm, the previous decision algorithm, only this time, once delta values are sorted. So sorting takes only n square times n plus n m log nm. Right? So in total, the algorithm looks like this. So in total, it takes n cubic m log nm, which is impractical still, because it's more than n cubic. But we have improved this now. In the plane, we removed the cubic even. Nm log square nm time. In that time, we can compute their discrete Frechet distance now by using some other properties, but that's a different story.
But in practice, n is small because that's the human where he is, right? And the m could be large because the dog it runs around.
Right.
Many cases, right?
Well,
it is practical.
The application of this measure doesn't need to be dog walking, but it's easy to explain the dog walking using, right? So this is how we make use of some properties, especially from discrete geometry, in design the efficient computational algorithm. Okay, this is the end of talk, and if you have any question, then feel free to ask any question.